How does a microwave oven work? A complete guide to understanding this kitchen marvel. The microwave oven has become one of the most common appliances in modern kitchens around the world. From reheating leftovers to cooking quick meals, this remarkable device has changed the way we prepare food. But have you ever wondered how this magical box actually works? How can it heat food so quickly without making the container hot? What makes it different from a regular oven? In this comprehensive guide, we'll explore the fascinating science behind microwave ovens, understand how they generate and use microwaves to cook food, and look at the exciting developments that are shaping the future of microwave cooking technology. The basic principle, understanding dielectric heating. At its core, a microwave oven works through a process called dielectric heating. This is a completely different approach to cooking compared to conventional ovens, which heat food from the outside in by warming the air around it. Dielectric heating works by using electromagnetic waves called microwaves to directly excite the molecules inside food. These microwaves cause certain molecules in food to vibrate rapidly, creating friction that generates heat from within the food itself. This is why microwave cooking is so much faster than traditional cooking methods. Think of it like this. Imagine you're trying to warm up a cold room. A traditional oven is like heating the air in the room and waiting for that warm air to gradually warm everything else. A microwave is like having tiny heaters inside every object in the room, warming them up directly and simultaneously. This fundamental difference in approach is what makes microwave ovens so efficient and quick. Instead of waiting for heat to slowly travel through layers of food, the microwaves penetrate into the food and create heat throughout its volume almost instantly. The heart of the microwave. How the magnetron works. The key component that makes microwave cooking possible is a device called a magnetron. This sophisticated piece of technology is responsible for generating the microwaves that cook your food. The structure of a magnetron. A magnetron is essentially a specialized vacuum tube that converts electrical energy into microwave radiation. It consists of several important parts working together. At the center of the magnetron is a cylindrical cathode that gets very hot when electricity passes through it. When heated, this cathode emits electrons, just like the filament in an old-fashioned light bulb emits light when it gets hot. Surrounding the cathode is a hollow circular structure called an anode block. This anode block contains several small cavities called resonant cavities or cavity resonators. These cavities are precisely designed to vibrate at microwave frequencies, specifically around a point for 5 GHz GHz. The microwave generation process. The process of generating microwaves involves a complex dance between electricity, magnetism, and electron movement. First, a high voltage is applied between the cathode and the anode. This electrical potential difference causes electrons to be emitted from the hot cathode and accelerate toward the anode, similar to how electrons move in any electrical device. However, here's where things get interesting. A strong magnetic field is applied perpendicular to this electric field. This magnetic field doesn't allow the electrons to travel in straight lines from the cathode to the anode. Instead, it forces them to move in curved, spiral, or cycloidal paths. As these spiraling electrons pass by the cavity resonators in the anode block, they interact with these cavities in a very specific way. The moving electrons induce radio frequency currents in the cavities, causing them to oscillate at microwave frequencies. The resonant cavities are designed to naturally vibrate at around a point for 5 GHz, which is the frequency used for cooking food. The interaction between the spiraling electrons and these cavities sustains high-frequency oscillations within each cavity. These oscillations generate the microwaves, which are then extracted from the magnetron through a coupling loop and directed into the cooking chamber via a component called a waveguide. This entire process is remarkably efficient at converting electrical energy into microwave radiation. The magnetron is specifically tuned to produce microwaves at the exact frequency that works best for cooking food. How microwaves interact with food. Once the microwaves are generated by the magnetron, they enter the cooking chamber where the real magic happens. Understanding how these electromagnetic waves interact with different types of food molecules is key to understanding why microwave cooking works so well. The microwave frequency. Microwaves operate at a frequency of approximately 2.45 GHz. This frequency was not chosen randomly. It represents a sweet spot that effectively heats common food molecules while avoiding interference with other electronic devices and communication systems. At this frequency, the electromagnetic waves oscillate to 0.45 billion times per second. This incredibly rapid oscillation is what causes the heating effect in food molecules. Inside the cooking chamber, when microwaves enter the cooking chamber, they don't just travel in one direction. The walls of the microwave oven are made of metal, which reflects microwaves rather than absorbing them. This means the microwaves bounce around inside the chamber, creating a complex pattern of electromagnetic waves. This bouncing effect is actually beneficial because it helps ensure that microwaves reach the food from multiple angles. However, it can also create areas of higher and lower microwave intensity, which is why most microwave ovens include a rotating turntable. The turntable slowly rotates the food, ensuring that all parts of the food are exposed to microwaves relatively evenly over time. Without this rotation, you might find that some parts of your food are much hotter than others after cooking. Penetration into food. Unlike heat from a conventional oven, which must work its way through food layer by layer, microwaves can penetrate directly into food. The depth of penetration depends on the type of food and its composition, but typically ranges from about 1 to 1.5 inches. This means that in foods thicker than a few inches, the outer layers are heated directly by microwaves, while the inner portions are heated by conduction as the heat spreads inward from the microwave. Heated outer layers. Why water, sugar, and fats heat up so well? Not all molecules respond to microwaves in the same way. The most effective microwave heating occurs in molecules that have what scientists call electric dipoles. Understanding why water, sugar, and fats heat up so effectively in microwaves helps explain why microwave cooking works so well for most foods. Water, the primary target. Water molecules are the main reason microwave cooking works so well. Water molecules have a very strong electric dipole, meaning they have areas of partial positive and negative electrical charges at opposite ends. When microwaves pass through food containing water, the rapidly oscillating electromagnetic field tries to align these water molecules with the changing field direction. Since the field changes direction to 0.45 billion times per second, the water molecules are constantly trying to rotate and reorient themselves to match the field. This constant rotation and reorientation creates friction between molecules, and friction generates heat. It's similar to how rubbing your hands together creates warmth, but happening on a molecular level at an incredibly rapid rate. Since most foods contain significant amounts of water, this makes microwave heating very effective for most cooking applications. The water molecules throughout the food are all being heated simultaneously, which is why microwave cooking is so much faster than conventional methods. Sugar, sweet and responsive. Sugar molecules, including the complex polysaccharides found in many foods, also respond well to microwave energy, though not quite as effectively as water molecules. Sugar molecules contain polar groups, particularly hydroxyl groups, which interact with the microwave's electromagnetic field. These polar groups cause sugar molecules to rotate and vibrate when exposed to microwaves, generating heat through molecular friction. What makes sugar particularly interesting in microwave cooking is its relatively low specific heat compared to water. Specific heat is a measure of how much energy is needed to raise the temperature of a substance. Since sugar has a lower specific heat than water, it heats up more quickly even though it may absorb microwave energy less efficiently. Microwave energy can also affect the chemical structure of sugar molecules, sometimes breaking chemical bonds and releasing smaller sugar compounds. This is why foods containing sugar can sometimes develop different flavors or textures when cooked in a microwave compared to conventional cooking methods. Fats and oils getting hot quickly. Fats and oils, including triglycerides found in cooking oils and animal fats, also absorb microwave energy effectively. These molecules contain ester groups that have molecular dipoles, allowing them to interact with the microwave's electromagnetic field. While fats don't absorb microwave energy quite as efficiently as water molecules, They have an important characteristic that makes them heat up very quickly. Fats and oils, including triglycerides, have a much lower specific heat than water. This lower specific heat means that fats reach high temperatures much faster than water when exposed to the same amount of microwave energy. This is why fatty foods often reheat or cook very quickly in microwave ovens, and why foods with high fat content can become extremely hot very rapidly. In fact, fats can become much hotter than water in a microwave oven, while water will rarely exceed its boiling point of 100 Celsius to 1 to F in normal microwave cooking. Fats can reach much higher temperatures, which is why they're effective for browning and crisping in some advanced microwave cooking. Applications: the complete cooking process. Understanding the individual components and principles helps us see how they all work together to cook food in a microwave oven. Step-by-step breakdown. The complete microwave cooking process follows these steps. First, when you press start on your microwave, electrical power flows to the magnetron. The magnetron converts this electrical energy into microwave radiation at a point for 5 GHz frequency. These microwaves are then channeled through a waveguide into the cooking chamber. The waveguide is designed to efficiently transfer the microwaves from the magnetron to the food compartment without losing energy. Once in the cooking chamber, the microwaves bounce off the metal walls, creating a complex pattern of electromagnetic waves throughout the space. This reflection helps distribute the microwave energy more evenly. The microwaves then penetrate into the food, where they interact with water, sugar, and fat molecules. These molecules begin rotating and vibrating rapidly in response to the oscillating electromagnetic field. The rapid molecular motion creates friction, which generates heat within the food itself. This heat then spreads through the food by normal thermal conduction, the same way heat spreads through any material. Why containers don't get hot? One of the most noticeable differences between microwave and conventional cooking is that microwave-safe containers typically remain cool or only become warm from contact with the hot food. This happens because most microwave-safe materials, such as glass, ceramic, and certain plastics, don't contain significant amounts of molecules that respond to microwaves. They don't have the polar molecules that absorb microwave energy and convert it to heat. The container only becomes warm through heat transfer from the hot food it contains, not from direct microwave heating. This is completely opposite to conventional oven cooking, where both the food and container are heated by hot air. The role of the turntable. Most microwave ovens include a rotating turntable, and this serves an important purpose beyond just convenience. The rotation helps ensure more even cooking by constantly changing the position of the food relative to the microwave energy pattern in the chamber. Microwave energy isn't perfectly uniform throughout the cooking chamber. There are areas of higher and lower intensity due to the way microwaves bounce around inside the metal box. By rotating the food, these hot and cold spots are averaged out over time, resulting in more uniform heating. Some advanced microwave ovens use other methods to distribute microwave energy more evenly, such as stirrer fans that change the microwave pattern or multiple magnetrons that create more complex energy distributions. Why metal objects should be avoided. Understanding why metal objects should not be used in microwave ovens requires understanding how microwaves interact with different materials. Microwave reflection. Metals are excellent reflectors of microwave energy instead of absorbing microwaves and converting them to heat like food molecules do. Metal surfaces reflect microwaves back into the cooking chamber. While this reflection is actually used beneficially in the construction of the oven, the metal walls reflect microwaves to keep them contained and help distribute them. Metal objects inside the cooking chamber can cause problems. Potential issues. When metal objects are placed in the microwave, several problems can occur. First, the reflected microwaves can create areas of very high energy concentration, which can damage the magnetron or other components of the microwave oven. Second, metal objects can create electrical arcs or sparks, especially if they have sharp edges or points. These arcs occur because the microwave energy can build up electrical charges on metal surfaces, and when the charge becomes large enough, it jumps through the air as a spark. Third, Metal objects prevent microwaves from reaching the food behind them, creating cold spots in the food that won't heat properly. Safe metal use? Interestingly, some metals can be used safely in microwaves under specific circumstances. For example, small amounts of smooth metal foil are sometimes used to shield parts of food from overcooking, and some microwave-safe containers have metal components designed to work with microwave energy. The key is that these applications are carefully designed to work with the microwave's energy patterns rather than against them. Advantages of microwave cooking. Understanding how microwave ovens work helps explain why they offer several significant advantages over conventional cooking methods. Speed and efficiency. The most obvious advantage is speed. Because microwaves heat food directly rather than heating the air around it, cooking times are dramatically reduced. A baked potato that might take an hour in a conventional oven can be cooked in just a few minutes in a microwave. This speed also translates to energy efficiency. Since microwave ovens don't need to heat up a large cooking chamber or heat the air inside it, they use significantly less energy for many cooking tasks. Nutrient preservation. The quick cooking times and lower temperatures often used in microwave cooking can help preserve nutrients that might be lost in longer conventional cooking processes. Water-soluble vitamins, in particular, are better preserved when cooking times are shorter. Convenience and control. Microwave ovens offer precise control over cooking time and power levels. Many models include preset programs for different types of food, taking the guesswork out of cooking times and power settings. The ability to start, stop, and check food during cooking without losing heat adds to the convenience factor. Current limitations and challenges. While microwave ovens are incredibly useful, understanding how they work also reveals some of their limitations. Browning and crisping. Traditional microwave cooking doesn't produce the browning and crisping effects that make many foods appealing. This is because browning reactions typically require higher temperatures than most microwave cooking achieves. The relatively low temperatures and moist environment in microwave cooking don't promote the chemical reactions that create the crispy, golden brown surfaces we associate with roasting, baking, or frying. Uneven heating. Despite turntables and other design features, microwave heating can still be uneven. This is particularly noticeable in dense or thick foods, where the outside may be hot while the center remains cool. Texture changes. Some foods don't respond well to microwave cooking because the heating method can change their texture in undesirable ways. Foods that depend on dry heat for their appeal, such as bread or pastries, often become soggy when microwaved. The future of microwave technology. The future of microwave cooking is exciting, with several technological advances promising to make microwave ovens faster, more versatile, and more effective. Inverter technology revolution. One of the most significant advances in microwave technology is inverter technology. Traditional microwave ovens work by pulsing on and off at full power to achieve different power levels. For example, 50% power means the magnetron turns on for half the time and off for half the time. Inverter technology changes this by allowing the magnetron to operate at continuously variable power levels. Instead of pulsing on and off, an inverter microwave can maintain a steady, lower power output. This results in more even cooking, faster heating times, and better preservation of food texture and flavor. Foods cook more gently and uniformly because they're receiving consistent energy, rather than alternating between full power and no power. Multifunctional capabilities. Modern microwave ovens are evolving far beyond simple reheating devices. Advanced models now combine microwave cooking with other cooking methods to create truly versatile appliances. Some microwaves now include capabilities for steaming, baking, roasting, grilling, air frying, and even sous-vide cooking. These combination ovens can replace several kitchen appliances with a single, space-saving unit. The integration of different heating methods allows these appliances to overcome traditional microwave limitations. For example, combining microwave heating with hot air circulation can achieve the quick cooking of microwaves, while also providing the browning and crisping of conventional cooking. Smart features and connectivity. The integration of smart technology is transforming how we interact with microwave ovens. Wi-Fi connectivity allows remote control through smartphone apps, enabling you to start cooking before you get home or monitor cooking progress from another room. Integration with recipe apps provides step-by-step cooking guidance, automatically adjusting time and power settings based on the specific dish being prepared. Voice control through smart assistants like Alexa and Google Assistant adds another layer of convenience. These smart features also enable automatic software updates, allowing manufacturers to add new cooking programs and improve performance over time. Advanced sensor technology. Built-in sensors are becoming increasingly sophisticated, monitoring multiple factors during cooking to automatically adjust settings for optimal results. Modern sensor systems can monitor moisture levels, humidity, temperature, and even the chemical composition of steam released from food. This information allows the microwave to automatically determine when food is properly cooked and adjust time and power accordingly. This technology minimizes the risk of undercooking or overcooking food and takes much of the guesswork out of microwave cooking. Hybrid heating technologies. The combination of microwave energy with other heating technologies is opening up new possibilities for microwave cooking. Some advanced ovens combine microwaves with infrared heating, which provides the browning and crisping that traditional microwaves can't achieve. Others combine microwave heating with hot air circulation, creating convection microwave hybrids that offer the speed of microwave cooking with the versatility of convection cooking. These hybrid technologies address many of the traditional limitations of microwave cooking, while maintaining the speed and efficiency advantages. Health and wellness focus. Future microwave innovations are increasingly focused on health and wellness applications. Steam cooking options preserve nutrients better than many other cooking methods, and pre-programmed healthy cooking modes support better meal preparation. Some advanced models include features specifically designed to preserve the nutritional value of foods while ensuring they're cooked safely and thoroughly. Compact and eco-friendly designs. As environmental concerns become more important, microwave manufacturers are developing more energy-efficient models that use less power while maintaining cooking performance. Space-saving designs are also becoming more important as living spaces become smaller and kitchen counter space becomes more valuable. New microwave designs are finding creative ways to provide full cooking functionality in smaller packages. Future interface innovations. Looking ahead, microwave ovens may incorporate augmented reality guidance systems that can provide visual cooking instructions overlaid on the real world through smartphone cameras or built-in displays. Advanced touchscreen interfaces are making microwave operation more intuitive, with visual cooking guides and interactive controls that adapt to the specific food being cooked. Conclusion. The microwave oven represents one of the most successful applications of electromagnetic technology in everyday life. By understanding how these remarkable appliances work, from the magnetron that generates microwaves to the way those waves interact with food molecules, we can better appreciate both their capabilities and limitations. The science behind microwave cooking is elegant in its simplicity. By using electromagnetic waves to directly excite molecules in food, microwave ovens achieve rapid, efficient heating that has transformed modern cooking. The interaction between microwaves and polar molecules like water, sugar, and fats creates heat through molecular friction, providing a fundamentally different approach to cooking than traditional methods. As technology continues to advance, microwave ovens are evolving from simple reheating devices into sophisticated, multifunctional cooking appliances. Inverter technology, smart connectivity, advanced sensors, and hybrid heating methods are addressing traditional limitations, while opening up new cooking possibilities. The future promises even more exciting developments, with innovations that will make microwave cooking faster, more versatile, and more effective than ever before. These advances will likely make microwave ovens central appliances in future kitchens, capable of handling a wide range of cooking tasks that go far beyond simple reheating. Understanding how microwave ovens work not only satisfies our curiosity about this common appliance, but also helps us use them more effectively and safely. As this technology continues to evolve, the fundamental principles of electromagnetic heating will remain the same, but the applications and capabilities will continue to expand, making microwave cooking an increasingly important part of modern food preparation. Whether you're reheating leftovers, cooking a quick meal, or exploring the advanced capabilities of modern microwave technology, you're participating in one of the most innovative cooking methods ever developed, one that harnesses the power of electromagnetic waves to transform the way we prepare and enjoy food. Thank you for watching. Like, subscribe and share. Stay tuned for more interesting videos.